Hey everyone.
Yeah.
Welcome back. So yeah, take it away.
Okay. All right. So I would like to also welcome everyone for being here again. And today's going to be the third part of the hypergeometric functions. And the plan will be today I'm going to talk about Galois perspectives. And so there will be some modularity results coming from hypergeometric Galois representations. And here are the setups that we kind of put up. In the previous two lectures, alpha will be a multi-set consisting of rational numbers. And the whole set is defined over Q if you look at the corresponding polynomial. Okay, let me see. Let me warm up my pen. Okay, that's ready. Oh, come on. If you look at this kind of polynomials, the x minus roots are unities because of the agreement of AI being rational numbers. If the coefficients are not only in cyclotomic field, but actually in Z, then it's said to be defined over Q. And moreover, a multi-set is said to be self-dual if alpha and minus alpha. That means you can negate the elements modulo Z. And a set of hypergeometric parameters consists of two multisets, alpha and beta. And because of the geometric origin, then we kind of set B1 to B1, or we can do the renormalization if necessary. And this couple is said to be primitive if the difference of any AI Bj are not integers. When I'm referring to a hypergeometric datum today, that means it's going to be a triple, consists of alpha, beta, two kind of multisets, and also there is a base parameter lambda. And when we get to representation, basically we would like Z in a good case to lambda to be in Z, or rational numbers, or some algebraic numbers. And in yesterday's talk, we introduced three notions of hypergeometric sums, which is the period function defined over finite field, the normalized period function defined over finite field, and there is also HQ function. In the primitive case, these two are the same. The difference lies in the HQ function can be extended, kind of get rid of the assumption on the Q, the size going to be 1 modulo the LCD, least common denominator. So this condition, you can get rid of that, you can replace, so you don't need this assumption for the HQ function when alpha, beta are defined over Q. Okay. So today we're going to see the perspective horizontally. Yesterday we mentioned the vertical perspective is basically locally for fixed P, you can build a zeta function. So we're going to go horizontally, and then the basic setup will be, again, we consider the least common denominators of AI and Bj, which is called capital letter M. And the corresponding field will be the cyclotomic field of Q joining primitive zeta, the answer of unity. The ring is going to be the ring of cyclotomic integers of that degree. And we are going to denote GQ to be the absolute Galois group. And for our convenience, we're going to denote, in this case, K is the cyclotomic field. We use G of M to denote the corresponding Galois group. And now P is, if I pick any non-zero prime ideals, in this ring, co-prime to M, we can build a quotient field by use the ring mod out by the non-zero prime ideal. And the size by the setup is going to be 1 modulo the least common denominators. So we're going to use Frobenius B to be the geometric Frobenius conjugacy classes. And so with that set, we're going to recall this is the period function.
Can I ask a question? Why do you want to invert M in the ring?
I do not. So if P divides M, you're going to get to, in terms of Galois representation, ramified cases.
Okay.
So here we consider unramified primes. Okay. So that basically when we get to the finite field analog, they are traces of the Frobenius elements. Right. And so in yesterday's lecture, we introduced the period function. So basically what we do is we fix a generator for the field, and we're going to consider in the case when your size is going to be 1 modulo this capital letter M, and all this kind of composition becoming integers. So you just consider, now you have characters, and characters. You have a trivial character down here, then you put into the definition from the period function, then you can compute the value. All right. So in this formulation, of course, it depends on the choice of the generator. For the normalized period function, there is a similar definition, but you're doing the normalization by dividing out some Jacobi sums to the front to get to the normalized period function. Okay. So let's first consider the kind of the basic case, which is the Legendre curve case. And when we pick lambda, which is a rational number, if we're avoiding 0 and 1, we put lambda inside here, say we consider -1 yesterday, we get an elliptic curve. So we get an elliptic curve, which is genus 1. So then we all know that in this case, for any L, which is a fixed prime number, we can consider from the L division points on the elliptic curve, we get to a Galois representation. And for good primes, that means P does not dividing the conductor, the traces of this Galois representation, as far as we can recall, will be P minus number of points. So now to count number of points, basically we get to this picture over here. If I put X into the finite field and look at the right-hand side, if it's going to be 0, I have one solution. If it's going to be a square, I can kind of compute 2 y values over finite field. If it's not a square and not 0, then I have no solution. So this formula 0, 1, 1, 2, 0 can be computed by using this combination. So this is the quadratic character, which is the Legendre symbol, and that will give you the same count as what I mentioned up here. So you sum over all the elements in the finite field, you pull out the major term, which is 1. There are p of them, and the leftover, the summation over this quadratic character is going to get us to the period function. Of course, in this case over here, the choice of omega, the generator, doesn't quite matter because after all, there is a unique quadratic character. So compare these two formulas, then we get to the conclusion, the chase, which is P minus this quantity down here, will be negative. Right? There is a negative sign. In general, there is -1 to the m, which is 2 right now, and -1. There is a sign. And then there's the period function. And if you write it down in terms of the normalized period function, the sign kind of will be dealt with correctly. There's no more sign. So there will be 1 here. But the difference down here, because I'm dividing some Jacobi sum, there will be some additional character. In this case, it's -1, the Legendre symbol coming in. But the Legendre symbol, we do not worry about that too much here because it's going to be global. That will be for all the choices of lambda, it will be the same. So the variation is actually coming from the second part if I vary lambda. All right. So this is actually the example telling you that basically the character sum, there's the period function up to a plus minus sign, or the normalized period function, they correspond to traces of Galois representations. Okay, any questions? All right. So here in this picture, we say that the choice for the generator doesn't quite matter. What it actually matters will be this character, and in this case, it's unique. It can imagine that when we move on to other m bigger than 2, actually what it matters will be there is a primitive order m character in the cyclotomic field. So it depends on which embedding you're talking about. All right. So that's referring to the notion that instead of consider finite fields individually, you're going to consider them in a consistent way. So we're going to vary the non-zero prime ideals, co-prime to m, to guarantee the residual field will be 1 modulo the capital letter M. So in this case, in each residual field, there is a primitive character, and they generate this particular subgroup over here. So when we actually put up locally, because now I'm going to vary this non-zero prime ideal, then the key point will be how to vary the choices for the generator. But basically, we don't need the performance of the generator. We only need to know where we send the primitive m through. So in this setting over here, globally, we're going to start with Q zeta m. We're going to fix 1 to start with. And essentially, when we see they're going compatible, will be basically for when you pass this element to the residual field, you're going to worry about which power, so which embedding you're going to get to. If I do not say anything, the agreement will be the power will be -1, all right, unless I specify otherwise. But altogether, there are phi that many choices for this power over here. But the agreement over here is without kind of specifying which one, the power, the generator for the multiplicative characters will send the primitive group to its inverse power. So this is the way that you can go. Basically depends on which prime ideal you give me. I can tell you which value the output will be. So this is actually a uniform way we can produce a lot of period functions. So let's kind of discuss a little bit about when the length of the multiset will be 2 in this case, which is actually very parallel to the discussion for the Legendre curve. So this is actually by the definition, this is the Euler integral formula. The normalized 2f1 function is going to be this integral with a normalizing factor. So this particular integral over here, as I explained, trying to draw the picture for the Legendre curve case, and you can replace 0, 1 by the Poch-Hamme contour integral if necessary. So this is going to be relating to a differential on such a ramified cover of CP1 ramified at 0, 1, 1 over lambda and infinity. So again, you perform the branch cut, right? You can cut along, last time I cut along 0, 1 and 1 over lambda and infinity. And now this time I'm going to use this many of them, all right? And in this this is the work before my current notation. So the capital letter N and capital letter M will be the same for the next few slides, all right? And so just like before, we use capital letter N over here to be the least common denominators of the parameter sets. If I choose I to be this choice over here, which is the least common denominator times 1 minus the rational number b, it's going to be an integer. And similarly, you can pick j to be these choices over here and k. Then this particular integral can be considered as a period on the corresponding very explicit unfold cover of CP1 ramifying at 4 points. And this curve over here, which is singular, we can actually consider its smooth model. And before that, we notice there is a built-in symmetry on such a curve, which will be the automorphism sending xy to x and primitive n through, the convention I also use this -1. This one of the primitive n through over here times y is going to be an automorphism, which is defined over Q joining theta. And there is a lot of computation into such kind of, we call generalized Legendre curve by the work of Wolfhard and Archnaut. She computed a lot of things very explicitly. And what we're interested in today will be the Jacobian of the smooth model. So we're going to use the superscript denotes which Jacobian we are computing from. So if we use so these two notions will be the same. We're computing the Jacobian of the smooth model of the generalized Legendre curve, which is up here, taking a smooth model. Then now for any proper divisor D, if I have a divisor, that means instead of taking, say, 6-fold cover, I'm taking double cover or third cover. Then if I replace this by D, this quantity by D, I will get a similar picture. So the corresponding Jacobian, when I replace this capital N by its proper divisor, I get to a, so you get to a factor, okay, which is isogynous. It's one of the factor or one of the quotient is isogynous to the O part, if we choose D to be a proper divisor. So then we can focus on the primitive part instead. The primitive part, according to Archnaut, if under also the non-degenerate assumption, non-degenerate means I want generically there are 4-point ramification instead of 3-point. Then in this case, she computed that the dimension of the generic part is going to be Euler free number of the least common denominator. So in the whole picture over here, if I choose lambda, which is a fixed value, and if lambda is chosen, say, for instance, defined over Q, avoiding 0, 1, what we get is actually in the whole picture, to start with, there is a Galois representation associated with the genus of this generalized Legendre curve. And for each divisor, you can compute the corresponding Galois representation, which is also for GQ. You take away those O parts. So the primitive part still give you pretty much a 2 times the corresponding dimension L at the Galois representation. In the theta over here, there are representation for GQ. So I have big chunk of Galois representation, but it's for a bigger group. If we use the action, this action I mentioned, the automorphism, which is on the curve, can induce a same kind of automorphism of the same order on the primitive part of the Jacobian. Then we can use this action to decompose my big Galois representation into pieces of the same dimension. So after you do the restriction, so this notation again will be the Galois group Q bar over the corresponding cyclotomic field Q joining zeta M. So the big Galois representation a priori is this dimensional divided into pieces. And it's going to be a direct sum of this many copies of 2-dimensional Galois representations. Right. So this is more or less the outline for how we attain the result, joined with very explicit description into what happens for generalized Legendre curve. So this is a result joined with Jenny Fuseli Ravi Ramakrishna, Holly Swisher, and Fountain 2. So basically, it says more or less, if ABC are rational numbers, and if we assume the least common denominator, again, is capital letter N over here, under the primitive assumption, if you go to this cyclotomic field, then if you use non-zero for any non-zero prime ideal co-prime to the discriminant, and for any L which is prime at your preference, then there will be a Galois representation, right? Then the A Galois, because the embedding I chose, will be sending the primitive root to its inverse, such that it's two-dimensional. And moreover, for almost all the good primes, there are some divisibility condition. I want the prime ideal to be not dividing denominator, numerator, denominator, yeah, and also 1 minus lambda. Then basically, when we evaluate the two-dimensional Galois representation at the Frobenius conjugacy class, what we're going to get to will be negative, the same as Legendre curve of the period function, when you're putting up things in this way over here. And in particular, we're going to look at what happens if the least common denominator, the corresponding Euler phi number is 2, right? So again, in this case, it will be actually the story will be we start with something which is 4-dimensional, which is 2 times the Euler phi number, which is assumed to be 2 over here. And so there will be a sigma lambda L. And then there will be a kind of the complex conjugate. The complex conjugate is actually the choice. I'm making the opposite choice. The first choice is sending the primitive nth root to its inverse, and its conjugate will be sending to the opposite choice. All right, so then we have 2 of those Galois representations, and 2 of the motivation for the next question, which is when does this 4-dimensional, the representation coming from this 2-dimensional abelian variety admits quaternion multiplication, right? So this is referring to something in the background of the arithmetic triangle group. Or the other motivation for myself is actually earlier I've done a paper with Olive Aitken, Winnie Lee, and Tong Liu. We discuss 4-dimensional Galois representations of GQ. Admitting quaternion multiplication, basically there is a quaternion algebra acting on the 4-dimensional representation. And there is an involution called I, there is another involution called J, and then they're anti-commutative. So after the paper's done, the referee asks us how many kind of cases you can come up with. So that was part of the motivation we're doing that. And the answer leading to one of the theorems that I mentioned in the first lecture, which is actually that by nature is describing when 2 of the beta function to be algebraic. All right, so the assumption here, of course, I'm choosing those values so that the Euler phi number will be 2, right? So this is where it is coming from. I want to actually mention about the idea, which is kind of putting some of the stuff I mentioned earlier together. So now we have, in this situation, the picture will be, there are 2 Galois representations coming in pair. And there is a sigma, there is a bar. The bar, actually the difference is between how you fix where you send the primitive nth root. And recall that if we look at the first guy over here, its trace, according to the previous result, it's negative, the 2p1 function, the period function. That means it's negative, the normalized period function, times there is a Jacobi sum. And now on the other hand side, I also have the same thing. I have negative sign, I have J bar, I have 2F1 bar. on the right-hand side as well. And now we're going to compare. The question essentially boils down to when they are different by a finite order character, which is the criterion that we, my paper with Winnie Lee Atkin and Tong Liu gave. It boils down to when they are different by a finite order character. So we compare them, and luckily for the 2F1 and 2F1 bar, because of the Euler transformation that I mentioned in both finite field and the classical case, especially for the finite field case, we know they are different by a finite order character. So that means the most difficult part is actually they agree up to a finite order character. So the remaining part will be the Jacobi sum. When the Jacobi sum different by a finite order character, and the Jacobi sum, of course, I mentioned they are finite analogs of the beta functions. Right? And according to Yamamoto's result, they are actually the only kind of relations among Jacobi's. I mean, Jacobi sum can be broken down into Gauss sums. Among Gauss sums, among a class of Gauss sums, there are only two relations, the refraction formula and the multiplication formula. So if I can make it into a finite order character, that means these two up to refraction and multiplication, they are the same. So they're up to algebraic multiples. So that's why it's actually giving why necessarily the ratio will be algebraic. And conversely,
Ling, can I?
Yes.
Can I jump in here with a brief question? Trying to understand the logic here. So you look at the finite field analogs of these, and you use Yamamoto to conclude that this ratio is a finite order character. Is that correct?
Yep. Yes.
And then somehow, this is the step I'm a little mysterious on. You now conclude that the complex analytic beta functions have a ratio which is algebraic. How does that logic work?
It's actually if I want, I mean the statement over here is E has QM, right? If and only if the ratio is algebraic.
Yeah. So I guess what.
So I'm not telling you this is algebraic. I'm telling you there are different cases. All right, there are different scenarios. There are two different scenarios. They might be very much different. That means the difference is not a finite order character, or they could be, as the example I showed you when I put 6431 case, IJK. In this case, it is. If I change the number, say I change that to something arbitrarily 66441, then the answer is not.
Yeah, okay. So my question is more general. It's you're going from the finite field characters, and then you're concluding something about the ratio of beta functions in the complex numbers.
Yep, indeed. It's essentially what Yamamoto tells you.
Do you understand my question?
What?
Maybe we should discuss this later. Okay.
Yeah.
Why don't you go on with your lecture?
All right. Okay. All right. So
yeah. Why don't you just go on and we'll talk about this later.
Okay. Yeah. All right. Maybe during the break or even after. All right. So the logic, it seems kind of weird to start with. But indeed, the Yamamoto's result in this current setting, it's only one direction, all right? I only know that if I have these choices making the two Galois representations different by a finite order character, then this ratio is algebraic, all right? Going the opposite direction, there is a result by Woosters. I actually attached it as an appendix to this slides, so just for your reference. All right. And now let's go to the general kind of setup. So this is it's a big book by Katz called Exponential Sums and Differential Equations. He actually talked about the whole l-adic setting compared to what Hammond's work. And in his setup, he's starting with, it's actually for individual local prime, P. Later, in a 2009 paper, he mentioned about there is a canonical twist you can perform so that the local pieces can be lifted up globally. All right, so once you do the canonical twist, then the whole setup can go from individual finite few results to global results. All right, so I'm not going to dig into the details that will require maybe a few or maybe a whole course on how Katz have done everything together. I only want to mention how his result can be stated in the way we understood. Right. So the setup now is give us alpha, beta, which are rational numbers. But we do need the primitive assumption to make our life easier again. So far, there is no other assumption other than they are alpha rational numbers, bi rational numbers, and primitive. And we have the same notion of the least common denominator. Then for any hypergeometric datum, all right, so here lambda is chosen to be inside the cyclotomic field of the integers. And then also I will line lambda to be not dividing the least LCD over here. Once you have this kind of combination, then what you can get, it will be immediately an l-adic Galois representation for the big Galois group. And it's going to be, so the space is going to be depends on which lambda you are picking. It's going to be over QL bar. And ramify almost everywhere. The back prime, one of the guaranteed back prime will be all the prime factors of M. And also there are possibly back prime coming from the lambda over here, but there are only finite many, right? And then the result continues for if you're avoiding the prime dividing M, and then there are some prime you should avoid, which will be those dividing lambda or dividing 1 minus lambda. If you're avoiding those, then you can look at this Galois representation. It's going to be, I'm going to talk about the dimension in the next page. It's a finite dimensional Galois representation. The key point will be the trace at the good prime P, the floor P trace is going to be up to a psi. There is possibly an additional order 2 character that you can actually forget because it's actually the same for everybody. So there is something like in my previous example, there is a phi or -1. There is additional quadratic character coming in. But the key point I want to make is then it will be the period function coming into here. And then also according to its notation, there is 1 over lambda. You can invert that or you can redefine, but this is compare the period function and Katz notation, there is 1 over lambda. All right. So the first statement we are making will be globally, if you have alpha, beta, which are given, you have a global lambda, then you have a Galois representation of the cyclotomic field, which is Q bar over the corresponding cyclotomic field into a QL bar space depend on lambda, such that when you computed the trace, what you will get to is the period function up to a correction sign and up to possibly additional quadratic character. Now let me talk about the dimension. So when the case you're avoiding, we are already assuming lambda is not 0, if it's not 1 as well, the dimension will be the same as the length of the alpha set. And it's more than that. Also, all roots of the characteristic polynomial, so you can, once you have a Galois representation, you can compute the characteristic polynomial as well. They are algebraic integers and have the same absolute value, which is going to be the norm of the prime ideal. raised to n minus 1 over 2. For the Legendre curve case, n is going to be 2. So what it says over here, you can, if I lambda is going to be in Q and P is a prime, then it's P to the 2 minus 1 over 2. So it's P square root P. So there are the eigenvalues will have absolute value, which is this corresponding number over here, under all the Archimedean embeddings. All right. So moreover, another claim is making, which is relating to what Beukers-Hammond's result regarding there is a notion of C, which is e to the 2 pi I gamma. Gamma is going to be minus 1 and the sum of bi, sum of ai. All right, so this quantity gamma. There are two situations which will actually see the monogenomic group inside, whether it's inside the SP or SO cases. The orthogonal group cases. So correspondingly, if you know that if it's the fiber is not 0 and 1, you know that your hypergeometric data is going to be self-due, then your representation space will admit either a symmetric or alternating bilinear pairing. It only depends on whether the multi-set alpha is going to be odd or even. Then you know that, which is corresponding to this C. If it's self-due, it's going to be either plus or minus 1. Okay, so it's plus 1. It's this case over here. If it's minus 1, it will be this case over here. And the other case that we use quite a lot will be when you get to lambda equals to 1. In the classical case, lambda equals to 1, the local monogenomic, the exponents will look like 0, 1, 2, all the way to minus 2, and then there is gamma. All right. So in this case, if you compute the corresponding Jordan block, it will look like 1, 1, 1, a bunch of ones. And then the last one, it's either minus 1 or the last one is going to be 1, and then there is 1 over here. So there are two situations, depends on C to be minus 1 or C to be 1. And accordingly, then if you look at the local monogenomic matrix, take away the identity, the rank, it will be 1. And then the result will be when lambda equals to 1, the corresponding Galois representation has a one-dimension drop. So it dropped down to minus 1. In this case, if you know the hypergeometric data still self-due, then you more or less have the same kind of conclusion, but it will actually tell you there is a sub-representation, which is primitive in the sense that the absolute value will be the same as before, but possibly there might be an additional kind of degenerate representation coming into the picture. The primitive part has an even dimension, and itself will also admit either a symmetric or alternating bilinear pairing depending on the alpha set length to be odd or even. All right, so for instance, if we look at n equals to 3 case, and this formula 2 times the floor function of 3 minus 1 over 2 will give me 2. So that means in this case, the representation at lambda equals to 1 will be 2-dimensional, and all the absolute value will be the same, which is p to the norm to the 3 minus 1 over 2. So it's the norm to the 1 power. If I look at even case over here, then this number will be 2. So the primitive part will be 2-dimensional, and then there will be additional 1-dimensional representation coming in. And the eigenvalue on this 1-dimensional space typically is smaller. All right, so this is actually kind of the Katz. He proved it in his book, and then what he did in individually for each finite field, then he put together after canonical twist to make it to be able to do it globally for all the primes. Okay. And now we're going to, basically what I'm like to get to is his formulation. So far, the representation is for this group is the absolute Galois group for the cyclotomic field. The next thing I want to explain will be what happens if the hypergeometric datum is defined over Q. All right. So before we continue, we'd like to mention basically, in order to consider alpha beta defined over Q, if I want to kind of lift the Galois representation from this smaller group to the absolute Galois group, what I want to use will be eventually there will be another version of hypergeometric function over finite field. It's the HQ function. The HQ function is the same as the normalized period function, but in this situation, the HQ function will be more kind of widely kind of defined for almost all primes. So before I get to that, I want to kind of recall how we did the normalization from the period function, which is used in the previous theorem of Katz. In order to get to the normalized version with dividing out by Jacobi sum, the only thing I want to kind of pay attention to right now will be the size. This size of the Jacobi sum a priori is going to be size square root Q, unless when I hit, say, any of the BI to be the trivial character. If I hit the trivial character, I'm talking about Jacobi sum of AI. In the primitive assumption, they are not trivial characters. Right? Under the primitive assumption, they are not trivial characters. And then AI bar. And it's easy to compute that. The size dropped down to 1. All right. So there is a behavior which is kind of, we have to be careful if BI is going to be the trivial character. Otherwise, they all behave uniformly. All right. So that gets into the next theorem, which is based on Katz's result and use BCM, which is the construction, the toric construction that I mentioned yesterday, giving you after the compactification, the major part, there will be a bunch of Q factors. The major part will be the character sum for HQ, right? So that was the result yesterday. So putting together the results as follows. So Katz tells you now you have a representation, which is for GM. And if alpha beta are defined, alpha beta including lambda are all defined over Q, then this representation is going to be invariant or is isomorphic to any of its conjugates if you use the quotient group G, which is GQ mod out by GM. Right. If you look at any of those elements, the coset, you're doing the conjugation by the assumption that alpha, beta, lambda defined over Q, they will be isomorphic. Right. So it tells you you can lift this representation down from GM and lift it up to GQ. And as we all know, such a lifting is not going to be unique. It's up to all the characters in the quotient group. Right. And the next statement is actually here is, yes, this guy can be lifted. There are different choices. Do I have a preferred choice? Oh, now I can tell you there is one choice, which is by the HP function. Because HP function corresponds to a global point count on a toric variety. So that I know that they will be globally compatible. So among all the choices, one of them we can use HP function. It's more than one lifting, but we're going to fix this lifting here. In order to use the HP function, we get to the finite field, the normalized finite field version here. But we have to be careful because of the different behavior I told you. There might be additional power of p to the 1/2, depending on here, the notation m will be, where's the m? Okay, n will be how many elements in beta are corresponding to trivial characters. They will give you a different count, all right? So that putting together what I want to convey is Katz representation is for the smaller group. It can be lifted up to GQ representations. Among the different choices, there is one choice at least we know how to compute exactly, which is use the normalized period function, which can be generated to HP function. HP function is global because there is a variety in the background. It corresponds to the counting, the motif coming from that toric variety. But you have to be careful. There is additional P power coming in because of the normalization. So this part depends on the normalization. And this is going to be the length of alpha set. N will be how many integers in the beta set. And in addition, there might be some other thing coming in. All right, there will be additional kind of normalization, finite order characters. But the major term will be this HP function. The HP function, however, the whole thing over here is integer, but the HP function may not be. I only guarantee it's going to be a rational number. Yes, Bill, you want to say something?
I'm just trying to read your formula. So trace your formula, trace of the Frobenius is phi of ma1, yeah. And then you have something else which I'm not quite sure what it means. Frob p
right,
chi.
so let me,
it's just some symbol for some finite order characters. Is that what you mean?
Yeah, there are some finite order characters I'm not going to concentrate on. So there is some finite order characters to the front due to the normalization. All right.
Okay.
So the key part will be this part putting together is the essential part.
Okay.
Corresponding to the normalized period function.
All right. Okay.
And
fine.
The normalized period function. Go back to the period function because Katz is using the period function. There might be additional power P.
All right.
So you need to put things together in a way so that they match up exactly. So the first statement is actually, now there is a lifting, which is we call the representation corresponding to the hypergeometric data with respect to this LAD field. The BCN over here means I'm going to use the BCN convention for computing traces. And the relation in between is this guy is for the big Galois group GQ. And after restriction, it will be the same as the representation we've seen before. And how to compute the unramified and unramified prime. This is the way to compute essentially. There is some fudge factor coming out from the normalization process, but the important thing will be the HP function. And a priori, it's not integer. You need to have a correct power P to make it to be integral. All right. And the last statement is basically concentrating on the case. If it's defined over Q, it's already self-due. And if it's 1, the situation will be the representation itself, there is also a one-dimensional job. And it also decomposes into the primitive part. Maybe there will be additional one-dimensional additional representation depending on n to be even or odd. But the primitive part will be, again, the same formula. It will be also admitting a symmetric or its alternating pairing depending on the parity. And on the primitive part, the representation is going to be pure. All the absolute value for all the roots of the characteristic polynomial will have for the primitive part will have the same absolute value under any embeddings, any Archimedean embeddings. All right. Any other clarification that you would like me to make?
Just one comment. You're looking at the behavior at lambda equal 1, and I claim it's pretty clear geometrically the dimension drops by 1 from the shape of the monodromy matrices, because what you're getting is the invariant part under the local monodromy. And if you look at the shape of that matrix, everything is invariant except a one-dimensional piece. So the dimension will drop by 1. That's my only comment.
Yes, yeah, that's what Katz actually attained. He actually related to the background, which is called the quasi-refraction, as what Bill mentioned. Right. All right, so this few slices actually is telling you that, hey, there's a very explicit way you can now construct our representations, and maybe it's a good place to take a break. So let's take a break over here.